This tutorial is to discuss different types of bonds. There are several objectives with chemical bonding. One is to explain why atoms form bonds, and this is partially to achieve the full shell look. In other words, to appear like a noble gas, and this then makes the atoms obtain a lower energy level because of the full octet. It's also used to illustrate how bonds are formed, the valence electron distribution in molecules and ions, and the molecular structures of the compounds. It's used to understand bond properties and their influence on molecular properties. There are three different types of bonds. One is the ionic, which is the complete transfer of one or more electrons from one atom to another, usually between a metal and nonmetal. Covalent, the sharing of valence electrons between nonmetal elements. So when we're looking at the periodic table, we have our diagonal line to separate the metals and nonmetals. If it's ionic, you're going to have something in here bonded with something up here. If it's covalent, both atoms are going to be coming from the right because they're both going to be nonmetals. And the metallic is the communal sharing of electrons between metals. So both of the atoms are going to be in the left-hand side. Molecular bonds are actually somewhere between covalent and ionic, and we'll be discussing that later. So here is a visual of the different types of molecules. Here's ionic, where the metal and nonmetal are alternating. So the positive of the metal and the negative of the nonmetal are really closely bound together. Covalent bonded, instead of having them all bound together, they have individual molecules that are close to one another. There's less interaction between the two. And the metallic bonding, you'll see that there's a metal, and then you'll see little circles around it. Those are signifying the electrons, and that creates a sea of electrons. So kind of like a swimming pool of electrons that the cations are sitting in. So therefore, just like water, the electrons can move around. So why exactly do atoms bond? And this is to achieve a full shell environment, so to be like a noble gas, to be more stable. The bond formed maximizes the attractive forces and minimizes the repulsive forces in the process. And the strength of the bond depends on many factors such as the type of bond formed, electronegativity, the size of the atoms, and the number of bonds between the atoms. Alright, I mentioned the word electronegativity in the previous slide. So what exactly is it? It's the measure of the ability of an atom in a bond to attract electrons to itself. So let's break down that word. You'll notice electron is in it. Also negativity is in it. Electrons are negatively charged. So the atom is becoming more negative with the more electrons it has, or the more electronegativity it has. This attraction or pulling of electrons causes the separation of charge between the bonds. This is now called the dipole moment, and it's based on polar opposites. Notice that we have a positive side here. We have a positive and a negative. This symbol is the Greek symbol delta. It's a lowercase letter, and we use it to mean the word partial. So what's happening here is fluorine is electronegative. So it's pulling the electrons towards fluorine. And as a result, there's more electron density over here, making this a little bit negative. It's not 100% negative. It didn't completely give up its electron to fluorine, but it's partially negative. And that's why we use this sign for partially negative. And what's happening then to the hydrogen is because the electrons are drifting from the hydrogen towards the fluorine, this leaves this to be partially positive. These are the two different ways of representing this. You can say that the electrons are drifting towards the fluorine, leaving the hydrogens a little bit positive. That's what that symbol means. And then the partially positive, partially negative symbols. You'll see this written in both ways, so you need to be familiar with both. The greater the difference, the more polar the bond. What we're meaning is the greater the difference in electronegativity from one atom to the next. So if there's a high difference, then there's going to be a high polarity. A dipole moment, which this is mu, another Greek letter, is a measure of the bond polarity. A dipole occurs when one side or end of the molecule is positively charged and the other is negatively charged. So notice up here, this is partially negative, this is partially positive. This is called a dipole moment when that occurs. This separation of charge can be caused by either the difference in electronegativities between the atoms in a bond or a cation-anion formation. It is directly proportional to the size of the partial charges and directly proportional to the distance between them. So over here we have mu. It's the charge times the size, the radius. Mu is measured in dBs, which is a capital D. Generally, the more electrons two atoms share, and the larger the atoms are, the larger the dipole moment will be. The percent ionic character is the ratio of the bond's measured dipole moment to what it would be if it were completely ionic. So if we look here, we're basically comparing the differences in electronegativity. So if the difference is 0, then it's a pure covalent bond. There's equal sharing of the electrons between atoms. There's a small range here where it's considered nonpolar. That means that the electronegativity is close enough that there isn't a real huge difference to make it, to warrant it being polar. This here, then, is actually big enough to be considered a polar bond. So that means the electrons are drifting towards the more electronegative atom. And then once it hits the 51% mark, then it's considered to be ionic. Here's a visual. At the very purest, the nonpolar covalent bonds, the electrons are being shared. Once those electrons aren't being shared equally anymore, the electronegativity is starting to grab more of the electrons. You'll get a partially negative and a partially positive area. And those electrons are not shared equally. And that's why it's called polar. And then once the electron actually leaves from one to the other, the electron is transferred and is now considered ionic. So let's look at the trend of electronegativity, so that way when you're looking at bonds, you can determine which is more electronegative and which one isn't, and where the electrons are shifting. Alright, so if you look at the entire thing, you'll notice that fluorine has the biggest number. Whereas over here, francium and cesium have the smallest numbers. That means fluorine wants an electron more than any other atom on the entire periodic table, while francium and cesium want it the least. You'll notice that the general trend, this isn't, once again, it's not 100% true, because there are exceptions. General trend is that the closer you get to fluorine, the more electronegative it is. The one exception, the biggest exception, is hydrogen. Notice 2.5 and 2.1. Hydrocarbons are extremely important in our lives. That's what our food is made of. That's what our bodies are made of. That's what trees are made of. Anything that's living has hydrocarbons in it. So if you look at the difference, 2.1 to 2.5 is bonded to a 2.1. This is carbon, this is hydrogen. That's only a 0.4 difference. That's right on the border of nonpolar. When carbon and hydrogen bond, it's considered to be nonpolar. So the hydrogen is the only one that's kind of tricky as far as the electronegativity trend. Alright, so let's break down what kinds of bonds there are. Atoms are close enough for their atomic orbitals to combine to make a bond. That's what's actually happening. So then you have to look at the electronegativity values of the atoms in order to figure out what type of bond it is. If they're close or very similar to one another, and then the atoms are in bonds. If they're metal bonds, if they're metal atoms, they'll be metallic bonding. If they're non-metal, they'll be covalent. But if it's covalent, you have to ask yourself one more question. What's the difference in electronegativity? If they're far apart, they're polar covalent. If they're very close to one another, they're non-polar covalent. So, the first time, you have to figure out if it's metals and nonmetals. If it's just one or just the other, it's either metallic or covalent. Then if you decide that they're both nonmetals, let's get a visual here. If they're both in this region, they're covalent. And then you have to decide how far apart they are from one another and determine if they're polar or nonpolar. If they're both in this area, that means that they're metallic. Now, the ionic is when you have one from here and one from here. They're very far apart. They're very different. They don't necessarily 100% of the time have to be in either one, but 90% of the time they will. Maybe even higher than that. And those are the different types of bonding.